All right, so I would have liked to discuss my solution to homework 4. Unfortunately, I didn't finish it. I'm working on what I think should be the proper way of implementing this in Rust. And having never done it in Rust before, I bit off a little more than I could chew. That said, homework 5 is out, and I will discuss my solution when it's ready. The problem, and I think, I don't know if the rest of you did it, but what made it a little extra difficult for me is, one, I want to make it as a library. So not bake in together application code and the library. The applications should just say like received, like you would with any normal program. And then I refuse to use any extra copies in Rust. It has to be casting just like in C. I don't know if you did that.
No, I did copy.
Right, and Rust is really insistent on wanting to copy things. Or at least wanting to kind of wrap a raw buffer in lots of little wrapper functions, and that's just no go. It's got to be cast this struct, just like you do in C, because that's the best part of C. I want to keep that in Rust, so I'll figure it out. Anyway, yeah.
Can you turn the light off?
Absolutely. And once I've figured that out, I think maybe we can spend a few minutes on a little bit of Rust in class so you can understand my code as well. I'm hoping it'll be beautiful. In the meantime, there isn't, the solution isn't that interesting in itself. There aren't that many cool tricks you can pull with this like little one outstanding packet solution. Let me show you the next homework. Let's see. Oh. So the next one is based on the previous one as promised. So basically we're extending the previous one, and you are more than welcome to extend your own if you like. Or if you don't like maybe you didn't finish it, then Alex had volunteered to share his source. So we will take his solution as a sort of a template if you want, and you can get started from that. Thank you. It's a fine solution. I think it passes the tests. It is not beautiful, but it's good. So that's another option. What we're doing is, and I will make that code available on here somewhere shortly. Okay, so what we're doing here is we're extending it to support a transmission window that is larger than one packet. Right? You could think of the original solution as having a window of fixed size of always one packet. And now we are sending, probably should think of it as bytes rather than individual packets, right? But maybe you have a 10 kilobyte transmission window, and you send everything that fits in that window. It starts at 0 at the beginning of the file, right? It goes 10 kilobytes in, and you send everything up to the end of the window. And then as soon as you get an ACK for anything, you move the window to the right. So now we've received the first packet, the leftmost packet. We already received an ACK for that. That means we don't need to remember that anymore. We can shift over by one, and now we can transmit one more packet, the rightmost packet. That's what cumulative ACKs are really good for, because now you might lose a few ACKs, but then you get an ACK for something in the middle, and that means, oh, I can shift the whole window up to sort of exclude that last one that was acknowledged. And cumulative ACKs, the way we do it in TCP, and I suggest you do the same, is you just say which is the next byte. So you acknowledge saying I've got everything up to but not including this byte. So the ACK says, oh, move your your transmission window up to this byte. Right? That's it. You're not actually moving things around, right? You're just adding numbers like the offset in the file or in the buffer. That's all we're doing. Okay, so that's the transmission window. But how big should it be? You could start out by having a fixed size and just see how it plays, right? But we're going to test this with lots of different speed of the links, right? Link capacities, different latencies. And as we learned in the midterm, the appropriate size of the congestion window is the product of the bandwidth of the bottleneck link along the path and the latency of the end-to-end path, right? Round-trip path. And so we can measure directly the latency, right? We have that already from the previous solution, but we can't, it's difficult to directly measure the bandwidth. So we'd sort of indirectly measure it by probing, just like TCP does. We try to quickly ramp up to sort of roughly the right speed, and then we slowly, additively increase the rate a little bit until we start dropping packets, and we drop quickly, and then we increase a little bit again. Right? That's the TCP model, and that's what you want to do for congestion control. So with transmission window, you could start with a fixed one, and we just want to see substantially better throughput on some nice links, right, than having a single packet, especially if it's long latency links. Short latency links, the transmission window doesn't really help. It doesn't do anything. You might as well send one at a time. But if you have several millisecond kind of latencies, then it'll make a big difference. At least if it's a high bandwidth link, right? Because it's the product that matters. Okay, so yeah, that's pretty much it for congestion control. The actual method, just like TCP, it's a good idea to use the same one, in part because it's good to kind of internalize how TCP does this, both for the purpose of exams and for the purpose of interviews and for the purpose of like understanding what's going on when you're out in the field. And it's also very convenient to not have to do it yourself. You can just kind of use the thing that lots and lots of people have worked on to try to improve upon but have failed. Okay, so we will test throughput. Of course, we'll check that the files are correct. That's the first, the high order bit. We'll check for throughput, and then we'll check for fairness. So if you have, if we have 2 or 3 of these ongoing pairs of sender-receiver and it's the same link basically, right? We have the sender and the receiver on the same machine in this case. We want to see that they get roughly the same throughput. So a good way to try that is you start a transfer on the same file, right? Twice. Start 2 transfers with the same file. If it's relatively long, like the transfer takes a few seconds, then they should finish at about the same time. Right? Then it's fair. It's very easy, if you don't do this additive increase, multiplicative decrease, it's very easy to end up in an unfair, unbalanced situation where one is always kind of reducing and the other one just kind of goes to some sort of max. Okay, and then as a sort of extra challenging test, we'll put your flow next to a TCP flow. So we'll just do a normal transfer with, say, NC. That's just a raw TCP connection from, in the same way that we have our sender and receiver. So basically with NC you can say, oh, send to this IP address this port, or you can say listen to this port, and it just takes it in from standard out. Takes it in from standard in, puts it out and standard out. NC is a great tool. So we'd want to see that this transfer takes about the same time as well. Yeah, that's roughly it. I think the most complicated is going to be just dealing with the transmission window. Like when you've lost when you lose a packet. Oh yeah, so we want to, just like TCP, we want to rely on losses. Let's see, where is it? Lost packet. I put this somewhere. Oh yeah, triple acknowledgement of the same packet. Let's count that as a loss, just like TCP does. So basically, when you receive a packet that is out of order, you acknowledge the same packet that you acknowledged before. You don't acknowledge the new packet because you're missing something in between. And you don't say, oh, I didn't get this one, because who knows. Or you just say, oh yeah, I actually have that other stuff. And you keep saying that, like, I have the other stuff, I don't have anything more. And then when you get 3 acknowledgements of the same thing, that means, oh, the packet that came after, that was supposed to come after, that one's lost. And at that point, you can start retransmitting. And so what's the reason that we do 3 instead of 2? I think it's going to be pretty limited on this homework. In the internet, it's because you have this common phenomenon of pairing links over particularly high demand links. They put 2 physical cables and they kind of load balance, like every other packet goes on every other link, and then they kind of get reordered by 1 very frequently. But being reordered by 2 is a very rare occurrence, so that's why they do with triple ACK. Okay, questions on homework 5? Due on Monday as requested, April 8th. So well after the spring break. All right, so in that case, I wanted to continue what we were doing last time. We were playing a little bit with routing tables, discussing static routing and sort of how things work on a real network. And I want to try a few more experiments, and we'll talk about some what's it called? Auxiliary protocols that are necessary in order to make the thing work. In particular, we'll talk about DHCP, Dynamic Host Configuration Protocol, and ARP, the Address Resolution Protocol. But first, we should return to the state we were in the last time we were doing this. And I was maybe slightly late for class because I was dealing with an incredibly mysterious behavior in Linux, and maybe we'll run into that too. Today, I was talking to both Professor Vamanan and Professor Stevens about this, and neither had a very good explanation for what's going on. Stevens has the best explanation so far. He says Linux is broken. I don't really believe it, but I'm starting to lean in that direction. So, no, usually that's not the case. Usually it feels like it's like that, but then it turns out you just misunderstood something. So we are on 2 machines, and we wanted to do this. We were pinging. I'll have some. I think I need some more windows. Let's see. Yeah. Okay. All right. So why don't we start with kind of a quick review of this routing table stuff. Oh. So this is what a router looks like on the inside. It's not a router we're talking to, but routers are the same as other computers. We have a list of destinations and a next hop for that destination. In the case the destination is all zeros, that means the destination is actually directly connected to us. Directly connected in the sense that it's on the same link layer network. So in the case of Ethernet, it's all Ethernet pieces connecting them with no router in between. So you can do a direct Ethernet to Ethernet transmission to reach the other destinations. So here we're saying, oh, this entire subnet, there's a net mask here, says the top 16 bits. Anything that starts with those top 16 bits are available at this network interface. So we can just send it out that interface and it'll reach the destination and we're done. There's no routing, further routing necessary. Same is true for anything with these 24 bits of prefix and these other 24 bits of prefix, 2 other network interfaces. So in total, the machine has 3 network interfaces. So these are the 3 subnets that the machine is directly connected to. And then there's the default route. If we look at it in numeric, it looks like this. So anything, and we say anything by putting this at all zeros. We could put anything we want in here, like it could be all ones if you want. Doesn't matter because the net mask here says like the prefix that consists of 0 bits. All right, that's the shortest possible prefix. So if it doesn't fit any other prefix, and in routing you always pick like the longest prefix match. So if there were several different choices, but one was a little longer, like it's specifically for one host, we'll pick that one. In this case, this is the shortest possible prefix. So we'll say, if nothing else fits, send it this way. And there it's a little special. So here we're saying, oh, that's the next hop router. In the other three cases, we know that the destination is adjacent. It's in one of the networks that we're actually directly connected to. But for everything else, we're going to have to rely on this other machine, which is connected to some other networks, which we don't know which they are, but we assume it has connectivity to everything else. Like, this is our best shot. Sometimes an IP address just isn't reachable, but this is still our best shot. It has a good internet connection. Okay, so if we wanted to try something, so if I say ping google.com, we were doing last time, it's going to try to send a packet to this address, right? Formulate an IP packet. Once it makes it into the, in this case, the Linux networking stack, right? It'll say, inside the kernel, it'll say, oh, that destination, let me look against all these routing entries, see which one fits. Actually, nothing really fits except this one. Okay, so that means we have to send it to this machine. So send it off there, and that machine was then responsible for delivering it onward. But we can tell it more specifically that I'm interested in, I wanted to do something different. So frames is my other machine here. And there's nothing special about that machine, it's just another Linux machine. Right, so now the routing table looks like this. So there's the address we were interested in, and we're saying I want to send it via this machine called frames. And here's the prefix, right? So this means for only that IP address. The prefix is the entire 32 bits. So this routing table entry applies only to this one specific address. Actually, while we're at it, let me try a different one. So I'll say I see. It doesn't like this syntax anymore. I'll go like this. Okay. What? Do I have to say that? Okay. So Linux is being nice. It's saying like, oh, you're probably making a mistake here. I have to tell it. It should be a net. Well, now I told it it's a net. Route add net. Or maybe I should have had zeros on there. Oh, there it is. Okay. Okay, so it's being, this command is just being very nice, making sure that everything kind of seems to make sense. So here I specified this long prefix that wasn't zeros, but then I gave a short mask. So that would have ignored these. And so it said, well, that's probably not what you meant to do. So let me, now it looks like this, right? So now anything that starts with this IP address will go to frames. With this prefix will go to frames. And I wouldn't actually need this extra entry. This is sort of subsumed by this other one. Okay, in fact, I want to delete that for now. Okay, so now I wanted to try pinging Google, ping this thing, and that's where we were last time. Huh. And there's the mysterious little behavior. And now I actually got a really nice response. I didn't see this before. It's so nice of it. Sadly, that kind of screws up my demonstration. Let me set this to 0. Yeah, I had it. Okay, let me try. We'll just try another IP address. See if we can get a. What is this? Come on. Oh. Well, that's the one we were working on. Yeah, okay. Sorry. So that one's working, but unfortunately it's not what we want. Okay, good. That will work. Okay. I will clean this up. Actually, why don't we put this back in? Okay, so that's better. Okay, that's where we were last time. It wasn't forwarding any packets, right? So I told it anything that starts with this, and now it's gotten confused. We'll talk about that maybe later on, but anything that starts with this, except for the one we were just working on, the 142, should go to frames. And it's being sent to frames, and we can take a look at that actually. Like that. Oh, did I give it the wrong IP address? Aha, 42. Let's do the 43. Right. Okay, so here they are. I'm sending lots of packets out from nodes to this, and that's actually frames. The reverse DNS lookup doesn't go to the right. It looks like a terrible one. Oh, sorry. No, that's not frames. No, this is Google. Still looks terrible. It should say Google here, right? But it's some other weird IP address. DNS name. Okay, so I'm sending this request, and I'm not getting any response. Right, and that's because it's actually going to frames. So now if I tell frames in the kernel, I just tell the kernel, oh, in fact, you should be a router. Like, you should be serving other hosts with nice requests, with this nice service, forwarding packets. Do that. And so now, because frames knows how to get to every destination, it can just forward it to the gateway. And let's ignore this piece for now. So at least in principle, this ICMP forward thing is what is the mystery that I wasn't able to disable it for whatever reason. But at least in principle now, frames is taking the packets from nodes and sending it onto the gateway, and then it comes back, and on the way back it'll go from the gateway directly to nodes. And the reason is that the gateway doesn't know anything about the fact that nodes send a packet to frames first. Like for the reverse direction, it's just looking for this destination. And it knows how to get to nodes, so I'll just use the shortest hop for that. Okay, so that's pretty much static routing in a nutshell. Right? Longest prefix match. You receive a packet, you look in your routing table, take the longest prefix match. Generally speaking, you always have a default route. Right? So if nothing else fits, you'll send it to the default router, and at home it's always like that. Always send it to the wireless access point. But if you're in a larger network, usually you have many different gateways for different IP subnets. Okay, but how do we find out? Like, how do we get it the last hop? So we are directly connected, right, to. Let's see. So in this case, it says, oh, send it to this gateway, right? That's what the routing table says. And then we know, based on so now we have to look up in the table again. Now we see, okay, here, that's the subnet that the gateway is on. So how do we get it? Well, we send it out this interface. That's fine. But it's not quite there yet, because we want to send it to a specific machine on that interface. There could potentially be tens of thousands of machines on one Ethernet segment. So we actually need to put in a MAC address, an Ethernet address in the packet if we want to send it to to this gateway. If you just send it out, well, in principle, Ethernet supports something called broadcast. So you can put all ones in the MAC address. And destination address, you say just a bunch of Fs. Right? It's a 48-bit address, so it goes F, and that's it. 6 double Fs. That'll work. Then it'll send it to every machine on the network. But that's kind of inefficient. Now every machine on the network receives it. The network interface card will say, okay, that's for me. I'm going to take it, deliver it to the operating system, and then the operating system sees, oh, wrong IP address, drop it. You don't want to keep doing that for every packet on the network. So we need to send it to the correct MAC address so that the network delivers it only to this one gateway that we want to reach on that local subnet. Let's see if we can make it a drawing. Is this the one? Okay, that's good. All right, so here's nodes. And the way an Ethernet network works is we have a switch in between. And they have these little Cat5 clever looking cables that kind of click in, can click them out. And so if I want to send something to anyone on this local Ethernet network, so here's another So a gateway is a router, meaning it has multiple network interfaces that it will forward packets between. So this over here is a different IP subnet, and this is all one IP subnet that we're on together, like that. Okay, so if I want to send a packet from nodes to frames, I don't need an IP header necessarily. I can send data directly to frames with just an Ethernet frame, but it's impractical. It's much better if we can use TCP, if we can use all the standard protocols. So everyone on here also, not this one, but all the normal machines on here, everyone speaks IP with each other just because that makes it look the same all over the world. Okay, so if I want to send an IP packet to frames, I need to know frames' MAC address. And the same is true for all other linked layers, unless it's just a serial cable that goes straight to another machine. Then you can just send it up because you know that's the only machine on the other side. But we need a way to find the address, the MAC address of frames in order to send it to frames. So, anyone have any ideas? I'll give you a hint. We can't use DNS, right? Because DNS requires IP, and this is something under IP. We need this in order to just get a packet to our router. Yeah?
Is the goal for both frames and nodes to discover each other's MAC address?
Well, they will need it if they want to talk. They don't necessarily need it like before they want to talk, but when it's time to talk. If nodes want to send a message to frames, it needs to figure out first what MAC address to send to. Yeah.
Could nodes like ask the gateway and say, hey, who's connected?
How does it send a packet to the gateway? It doesn't know the gateway's MAC address. Ooh, okay, so here's one way you could do it. You could have the system administrator configure for every IP address on the subnet, what is the MAC address? Right? That would work, but it's a lot of work, and we'd rather not.
Well, when nodes connect, shouldn't the gateway say something?
Gateway doesn't even notice that anyone connects. When you connect to a switch, nothing happens. A light goes on, right? But there's no packets being exchanged. Nothing is sent to anyone unless this machine here says, like, tries to send something. Right? And then something can happen. But it doesn't know where to send it to yet, right? Doesn't have a destination address. So
We can't broadcast?
yes, we can. Okay, getting somewhere.
So broadcast everyone and ask who's out here.
Okay, who is out here? Yeah, that would probably be okay, but it could get a little noisy if you have a lot of machines. And we don't want to talk to all of them necessarily. But I think you're on to something.
Who's the gateway?
Yeah, and in particular, who has this IP address, right? We want to reach this IP address. So we send a packet out, an Ethernet packet out to the broadcast address, all Fs. And we say, okay, and I am this, right? In an Ethernet packet, just like in an IP packet, there's a source address and a destination address, and then there's a protocol saying what's coming next. The IP header is coming next, right? So the source address is us, so we can get a directed transmission back to us. And then the destination is a broadcast address, so everyone gets this. So now we're asking, oh, does anyone have this IP address? And whoever has it sees the request and sends back the response. Let's see if we can get that to happen sort of live here. Maybe okay, protocol ARP. No, okay. I'm worried that I will get too many packets on the screen, so I have to figure out how to filter this out. ARP, yeah. Okay, that's good. Okay, that might work. Okay, so now I just removed, ARP is the protocol for this, and I just told it, like, forget all about frames. So here's our ARP table right now. This is everything we know about the local subnets. All the IP addresses we've observed, and nothing's in there. And so if I want to now ping frames, we need to find out this MAC address. Come on. Well, it's in there. Why didn't we catch it? Okay, let me Google for this. Where's TCP dump? Here. Well, here it says you can say ARP. Let me try that again. Okay, now it's okay with it. All right, there's a lot happening here apparently. Because this is a relatively large subnet. So we'll just look for just packets about frames. Let me delete this old one and try another ping. There it is. All right. Okay, so a packet went out. And I'm capturing this now with -e. That's show the Ethernet headers as well. That's what you're seeing here. So we're saying from our MAC address to the broadcast address. TCP dump was clever here. It replaced all the Fs with broadcasts. If I had said -n, we would have gotten all Fs instead. So we're sending this request to everyone. It's an Ethernet frame with a type, a protocol type, 806. And we're asking, who has the address? And this, again, was clever. Actually, the IP address was in there. It wasn't the MAC address. No, sorry, it wasn't the DNS name. Maybe we should just do this again so we get the it numeric. Otherwise, it seems pretty confusing. Oh, but then grep frames isn't going to work, is it? Let's go like this. Oh, that won't work. All right. Try another ping. Okay, good. Okay, so everyone who's got this address, that's Frame's IP address, tell me, right? So we get a couple of things with this message. We're saying, oh, this is our MAC address. And at the same time, we're also saying, oh, and this is our IP address, right? So the response can come back very nicely. It'll say, here, this is sent to us, right? That's our MAC address. And someone is responding. It doesn't actually have to be Frames that's responding. Anyone who knows can respond and say, okay, this IP address is at this. So here Frames is responding directly. And now Frames actually knows as well, right? Because it just received a packet with someone saying, like, oh, let me know, and here's my MAC address. Right? So now Frames has a mapping, so it can do IP routing back to us as well. This is a little bit dangerous because it's not authenticated. So anyone can respond with whatever they want. Right? You can say, yeah, I'm that IP address. And in fact, that's often how it works. Like that's a common attack on an Ethernet network. If you want to snoop on someone else's traffic on the network, you will just say, yeah, that's me. Right? And you keep getting copies, you keep getting that data. Now, usually the other machine will detect that there's a problem. So it'll put up a warning message or something. If it doesn't, then basically you get all the traffic instead. So now it kind of isn't that practical. There's another way you can trick the switches to send it to both of you, but we can skip that for now. Okay, so there's ARP. Very simple, and the purpose then is to look up the MAC address for an IP address that's on your local subnet. Nothing else. You can't look at a MAC address for this Google server. That's like Ethernet frames don't make it beyond our local subnet. Yeah.
But if we get conflicting responses, like you said, this is an attack, so if the attacker is advertising, then the actual machine would also be advertising. Yeah,
right. So there's no particular standard for how you're supposed to deal with that. You're not supposed to do that. If you, yeah, and then you can send more packets, and then it'll change its mind. So you can kind of at any given time you can kind of take that over. If you're really paranoid about it, you can manipulate your ARP table directly. So you can statically configure that this IP address, that MAC address, and then it's not going to change. Most people don't do that. I think usually it's a better idea to not let people you don't trust onto your subnet, right? So this applies particularly well to open Wi-Fi access points, right? If anyone can get on, then anyone can send ARP messages, and anyone can get your traffic to their machine. If it's encrypted, yeah, it's good that it's secret and all that, but it's also that only people who you have given a password to can be on the network and can actually send these messages. It's not possible to send a message to the network without knowing the password. So that's quite practical. In a physical network, you just try not to make the connection, like the plugs, available to attackers. That's pretty much it. Unfortunately, they tend to just take over a machine through some malware or whatever, and then they're on their network anyway. So it's kind of limited. There's only so much you can do, I guess. You really need to protect each machine from attack, and that's a topic of a different class. Okay, so yeah, the ARP table is very important to understand this distinction here. That when we're sending an Ethernet packet, it goes from here through the switch. The switch is a layer 2, a link layer device. It only looks at the destination MAC address. So the Ethernet frame goes from here to here, but after that we shave off the Ethernet header. That's gone. The gateway router looks at the IP header to see where to send it next and puts on a new Ethernet frame. If it's Ethernet on this side, puts on a new Ethernet header at the top and forwards it on. So you would never see any sort of Ethernet addresses from outside of your local subnet in your packets. You can't do an ARP for a remote Google kind of a Google host. Okay, any questions on this before we move on? I would really encourage more questions in class. I think questions are great. It makes it much more interesting, especially when I don't know the answer. Okay, so there's one other little piece that's handy that isn't quite as necessary. And that is, what's my IP address? Right? If you have a server like these guys, these nodes and frames, they're, expensive server, you put it in there in the big rack, and it's okay that you configure it manually with an IP address. So someone puts in the effort to figure out which number should I give this one. That's okay. But it's not okay when someone comes in a cafe with their laptop and they just want an IP address so they can check their email. So we need to solve that some other way. You don't want the barista kind of handing out IP addresses. So the solution for that is called the Dynamic Host Configuration Protocol, DHCP. You may have seen this. And it works something similar. So, in fact, maybe we should see if we can get a nice picture. Yeah, there's a lot here. Okay, this one's pretty good. So with the purpose of DHCP, it serves all sorts of different functions, but the main one is just tell a new visitor to the network its IP address and the net mask. It needs to know the net mask because otherwise it doesn't know how to broadcast to an IP subnet. Right? If it's a 20/24, an 8-bit subnet, then the broadcast address, maybe we didn't talk about this, but the broadcast address for this network, if you want to reach every IP address on the subnet, is the network prefix and then all ones after. So you can ping, like, let's see what happens actually. Let's try pinging this. Yeah, it's a good question. I mean, it's not really something you usually would want to do. Huh. It's not very impressive. Let me try it. No, it's okay. I'll just leave it. So it looks like the broadcast didn't broadcast the way I would expect. In this case, only the gateway responded. Maybe it's the case that all the other Linux machines are configured not to respond to a broadcast ping. And that's reasonable. Like, you wouldn't want to do that, really. But it's good for the gateway to do it. It's nice. Yeah, in any case, you need to know the net mask and your IP address, and then you're good. Oh, and you need to know the gateway, right? You need to know who is the default gateway to send packets to the internet. So those three things we really need to get. With DHCP, you send a broadcast packet, right, to the Ethernet, to the local Ethernet segment, and so far you don't even have an IP address. So you send it to the global broadcast IP address. It's 255.255.255.255. It just means like, oh, I don't know where I am, but let's just send a packet to everyone on this subnet. That's it. So, and that translates directly to this all Fs Ethernet MAC address. So you send a packet saying, okay, I'm a DHCP client. I need a server, right? That's the discovery thing. And the server, and I need an IP address, I guess. That's what you're saying. A server, there could be multiple servers on the network. They respond back saying, okay, here you go. Here's an IP address. This is your net mask. This is a gateway. And because there could be some little race conditions here, and there could be multiple DHCP servers potentially on the network, the client then says, like the one that they wanted. Say, yeah, okay, I like that one. So it requests that. And then finally the server says, yeah, fine, that's yours. And then you own that for some period, say a day or an hour or something like that. There's a timeout configured in the entry or in the offer. So now you can automatically then set your IP address to whatever is in the DHCP request and live with that for a while. Yeah.
So if there was a conflict, like two clients both want to request the same IP, does the server say like you can't have that one? Here's a different offer?
Right. Yeah. So it can be denied. Okay. Right. And then you'll just try again. And an IP address can also be retracted. There's a few other extra steps. We'll have to look at this later. But these 4 steps are required. Like discover, offer, request, acknowledge. Then you have it. And after that, there's like, oh, I want to kind of renew my lease on this IP address, or the server wants to take the IP address back, that sort of thing. That's important. Well, maybe we'll look at some details next time. Okay, so there you have it. Now we have all the pieces necessary to do internet routing, as long as we don't want to dynamically do any routing. Like we just have static routes configured for every destination. Yeah?
What were the 3 things that the DHCP needed?
Yeah, IP address, net mask, and the gateway.
It itself needs an IP address?
Sorry.
You said IP address?
So the client, the DHCP client, the new guy coming in.
Oh, so the server doesn't need those things?
The server has a list of available IP addresses configured. It knows its own IP address. That one's set up by an administrator. What the point of the DHCP protocol is new temporary visitor kind of automatically configuring when you open up the laptop. Okay, cool. Have a good spring break, everyone. I'm off to the Caribbean.